Okay, thanks Jessica for introduction, and it's a great honor to speak here. And so today I'd like to introduce our Clipper, which is joint work with my lab mate Yilin. So we want to propose the p-value free FDR control method on high throughput data from two conditions. So we want to look at the high throughput biological data, where high throughput means there are a large number of features. So here features can be genes, proteins, and genomic regions. And for such data, often we only have small sample size, and we want to contrast two conditions, one experimental condition and one background or negative control condition, to identify some interesting features. So here I'd like to show some example of such high throughput biological applications. The first one is peak calling from ChIP-seq data. So in peak calling, the feature is a genomic region. So for example, the yellow beans here, a feature is interesting if it has higher peak in the experimental condition than the background condition. And the next example is called peptide amplification from mass spectrum data. So here the input will be the mass spectrum, and we will use search algorithms to match these mass spectrum with a target protein database and the decoy protein database. The match between the mass spectrum and target peptides are called target PSMs, and the match between mass spectrum with decoy protein database is called decoy PSMs. Then each feature will be a PSM, and a PSM is interesting if each matching score is higher from the target peptide than from the decoy peptides. So, and the next application is the differentially expressed gene analysis from seq data. So here we have two conditions. For each condition, we have 3 samples. Each row is a replicate and each column is a gene. So here we want to identify those interesting features or interesting genes while the gene expression values are different between the two conditions. For example, this one, and such genes where the expression values are similar between the two conditions are uninteresting genes. So, and our last example is the identification of differentially interacting regions from high-C data. And here is the data. So actually, it is a rotated up triangular matrix where each row and each column is a genomic region, and each entry in this matrix is a pair of genomic regions, which is a feature in this analysis. The values in each entry is the intensity, the interaction intensity between the region pairs. And we want to identify those region pairs where the intensity is different between the two conditions. For example, these regions. So from all these examples, we can see that in all these applications, we want to identify some interesting features where interesting can be either enriched or differential. The enriched features are those features which has higher values in the experimental condition than in the background condition. So for example, in the peak calling and the peptide amplification. The differential features are those features which has different values between the two conditions. For example, in the DE gene analysis and the DIR analysis. In all these, for all these interesting features, when we discover them, we want to control the false discoveries, because we want to make our discoveries as reliable as possible and also to reduce the validation cost. The most widely used criterion for controlling the false discoveries is called the false discovery rate. And it is defined as the expectation of the ratio, which is the number of false discoveries over the number of total discoveries, which should be at least 1. And although there are also some Bayesian paradigm for the false discovery rate, in our work, we mainly focus on the frequentist FDR. To control the FDR, there are some popular methods, and most of them use the p-values to control the false discovery rate, including the Benjamin-Hochberg or BH procedure or Story's Q-value procedure. For both methods, it requires the p-values, and to calculate the p-values, it requires either the distributional assumptions if we use parametric test to calculate the p-values, or it requires a large number of replicates if we use non-parametric tests to calculate the p-values. And for the approaches to calculate the p-values, we categorize the approaches into paired and pooled, and I will introduce these two approaches later. For the paired approach, it is used in the p-calling, the peptide identification, the DG analysis and the DIR analysis. So this is diagram for the paired approach. So the left columns are from one condition, and the right columns are from another condition, and each row is a feature. So for each row, we look at one feature at a time, and for each row, we can do a 2-sample test to get a p-value. And then given all the features, we get all the p-values, and then we can use the BH or Q value to set a cutoff on the p-values. However, there are some issues about the paired approach. The first one is called misformulation. So for example, the 2-sample test is mistaken as 1-sample test, and I will show an example in the following slide. The second issue is called modal misspecification. For example, when the real data comes from the Newton binomial distribution, but we use a Poisson distribution as a model. This model misspecification is a problem, especially when we have few replicates. So in that case, it's very hard to specify the correct model. And here is an example of misformulation, and it is from a very famous p-coding method called MAX. So from the method section of that paper, we can see that it first estimates a Poisson lambda from the control sample and use that lambda to calculate the p-values for each genomic region in the experimental sample. So which means that it ignores the randomness in the control sample and mistaken the 2-sample test as 1-sample test. So although it has very, very apparent mistakes in their method, it's still very popular in the p-coding field. And now let's come to the pooled approach. So the pooled approach is used in the peptide identification from the mass spectrum data. So if we still look at this data frame, so the right columns are from the background condition, and for each feature, we calculate the average of that feature and pull all the averages into a null distribution. And for each feature in the experimental condition, we can still calculate the average. And for each feature J, we can calculate its p-value by looking at the right tail probability in the null distribution. Still, we can get all the p-values for all the features, and we can use the BH or Q value to set a cutoff. So from this method, we can see that the pooled approach assumes a homogeneous background, which is likely violated in biological data, because for different features or different genes, they may have different distributions. And for the paired approach, so we can still see the model assumptions, especially the parametric distribution assumption, are also likely to be violated. And this is the motivation for our proposal Clipper. Before introducing Clipper, there are also some methods which do not use the p-values, but use local FDR, which approximately control the false discovery rate, but using the Bayesian paradigm. And I will not go to the details of the local FDR methods, but generally it summarizes the measurements from the two conditions into a statistic and estimate a local FDR by estimating the null distribution of the test statistics. And the null distribution are usually based on normal assumptions. So according to the fact that existing methods mainly based on parametric assumptions or homogeneous assumptions, we propose our clipper, which does not use p-values, and it does not assume parametric distribution because we think the p-value assumptions are likely violated in biological data. And we also does not require many replicates. There are two key components of our clipper. The first is the definition of contrast score. So here the contrast score is defined for each feature, and it summarizes the measurements from the two conditions. And second component is the cutoff on the contrast scores. So we control the FDR by setting a cutoff on the contrast scores, and the cutoff are borrowed from the BC procedure by the Novel paper by Barber and Candice, and we also use another cutoff from the GZ procedure by Jimenez and Zhou. And we want to show that by getting rid of the p-values and parametric distributions, our clipper method is robust to distributions, number of replicates, and outliers. And here is why we call our method clipper. First, we only want a small proportion of discoveries, which is like a nail clipper. And also we are in LA, and there is a basketball team called LA Clippers. And here is a cartoon to illustrate our clipper method. So here we still have the same data set. We have several replicates from one condition and several replicates from another condition. And we calculate a contrast score for each feature. And we hope we see such a distribution for the contrast scores. So we hope that for the uninteresting features, the distribution of contrast scores should be something symmetric around 0. And for the interesting features, the contrast scores will be this heavy tail. And so that we can use the BC procedure to control the FDR. And I'd like to briefly introduce the method of our clipper paper. And so first is some brief annotations. Here, D is the total number of features, and XJ and YJ are the measurements from the experimental and background condition. And all those values are above 0, which is the case in most biological data. And we also define mu xj and mu yj as the expectation of the measurements for feature j from experimental and background condition. And feature j is interesting in enrichment analysis if mu xj is greater than mu yj, and interesting differential analysis if mu xj not equal to mu yj. The definition of contrast score are different in different analysis tasks, including enrichment analysis with m equal to n, enrichment analysis with m not equal to n, and differential analysis. Due to time limitation here, I will also only introduce the most simple case, the enrichment analysis with m equal to n. So in this case, we first define two summary statistics, T-diff, and which is a difference statistics. It is just for two input vectors x and y. It is just defined as difference in means of the two vectors. And the T-diff, which is maximum statistics, it is defined as the maximum of the two vector means times the sign of x bar minus y bar. So which means that when x bar is greater than y bar, T max is just x bar. And if x bar is smaller than y bar, this is just negative y bar. And then the contrast score of feature j is just defined as T-diff xj yj, which is a difference contrast score, or T max xj yj, which is a maximum contrast score. So we can see that the definition of the contrast score is very, very straightforward and simple. And based on these two contrast scores, so here is a cartoon showing how we define the contrast scores. So here is the first one is an interesting feature. The measurement from the experimental condition is 10, and from background is 0. So the maximum contrast score is the maximum of these two values, which is 10. And for the uninterested feature, the maximum of these two values is 2, but the experimental is smaller than background, so it is negative 2. And the difference contrast score is just the difference between the measurements between the two conditions. So it will be 10 minus 0 equals to 10 from the interesting feature, and 1 minus 2 equal to negative 1 from the uninteresting feature. So given all the contrast scores, we can define our cutoffs on the contrast score as follows. So first, we define a set of all the candidate cutoffs as all the absolute values of contrast scores, and then define the TBC, the cutoff, as the minimum of all the candidate cutoffs, which satisfies that the number of contrast scores smaller than negative T over the number of contrast scores greater than positive T, smaller than equal than 0. So it's more equal to Q. So here, we can just consider it as something similar to the false discovery proportion. And this is similar to the number of false discoveries, and this is the number of total discoveries. And given this definition of the cutoffs, we have some theoretical control of the false discovery rate. And if we have the number of replicates different between the two conditions, then we will introduce some permutations. So here I will not go to the details, but briefly, we will first permute the replicate between conditions, and then calculate a degree of interestingness for the original feature and the permuted feature. And then we will summarize all the degree of interestingness into maximum or difference contrast scores. So if you want to see the details, you can refer to our paper. And now I'd like to show some results. So first, we did some very comprehensive simulation analysis considering different number of replicates, different distributions, different number of features, and we also consider both homogeneous and heterogeneous background. And we compared Clipper with p-value-based methods, which is a combination of p-value calculation approach and p-value thresholding procedure. And we also compared Clipper with local FDR-based methods. So the first result is on the 1 versus 1 enrichment analysis, which means that we only have one replicate from each condition. So from the results, we can see the x-axis is target FDR and the y-axis is the actual FDR. So we should expect that the FDR values are below the diagonal. And from the results, we can see that when the number of features is small, the pooled approach cannot control the FDR when we have small target FDRs. And for the large number of features, the BH pooled procedure cannot control the FDR when the model assumption, the homogeneous background assumption, is violated. And if we go to the power, we can see that among all the methods that can control the FDR, which are the methods that are left to the vertical line, so Clipper has the highest power among all the methods. And we also look at the 3 versus 3 enrichment analysis. In this case, we include the paired approach with the correct model specification, which means that we use the correct model, but still we can see that even when we have the correct model specification, it cannot control the FDR when we have outliers. And in terms of power, it still have less power compared to Clipper. And Clipper is still the method with the highest power among all the methods that can control the FDR. And we also look at some other distributions. And one interesting discovery is that when we look at the 3 versus 3 differential analysis, we can see that even though when we don't introduce outliers, the paired approach cannot control the FDR even when we correctly specify the negative binomial distribution. It is because when we only have 3 replicates, it is very hard to accurately estimate the 2 parameters for the negative binomial distribution. So still if we look at power, we can still see that the Clipper achieves the highest power among all the methods that can control the FDR. We further compared Clipper with some non-parametric tests, for example, the Wilcoxon test and permutation test in a 10 versus 10 enrichment analysis. So here we only include these non-parametric tests in 10 versus 10 because they totally lose power with smaller number of replicates. And from these results, we can also see that Clipper achieves higher power than these non-parametric tests together with the BH procedure. And here the parametric means that we use the correct model specification. Okay, so here we have used simulation results to show that Clipper is very powerful theoretically, and we also applied Clipper in many high-throughput biological data applications, including all the 4 applications I introduced above. The P-calling, the peptide amplification analysis, the DE gene analysis, and the DIR analysis from high-C data. For all these applications, we compared Clipper with some very popular existing bioinformatic tools. So let's look at the first application, the P-calling from ChIP-seq data. So here we compared Clipper with 2 very popular methods called Max2, which is a latest version of the Max paper, and another one is called Homer. Here we use Clipper as an add-on of these 2 methods, and from the left panel, we can see that without Clipper, Homer and Max2 cannot control the FDR well, especially for small target FDRs. But with Clipper as an add-on, it can control FDR without much loss in the power. And second application is the peptide amplification from the mass spectrum data. And from this, we can see that although another method, mascot, can control the FDR, it has smaller power than Clipper. And we also look at the DEG analysis where we compare the Clipper with DSeq2 and HR, which are the 2 most popular DEG analysis tools. And the result shows that the DSeq2 cannot control the FDR, and the HR has lower power compared to Clipper. So even with IHW, which is a method which can boost power by incorporating other feature covariance. So we also look at why DSeq2 cannot control the FDR, and by looking at the p-value distributions of the most frequently identified DE genes that are actually not true DE genes. And from the distribution, we can see that the p-value distribution are not uniform at all. So which means that the model assumptions for DSeq2 are likely violated, and it causes unreliable p-values, and it makes the FDR control failed for their method. And we also use some real data to try to illustrate that the DE genes identified by Clipper are more biologically meaningful. And we also use the single-cell data, simulated single-cell data, to compare Clipper with the HR, t-test, and Wilcoxon. Here we include these 3 methods because they are shown to be more reliable from a benchmark paper. And from this result, we can also see that Clipper controls FDR, and receive and achieve very good power. The last application is the DIR analysis from high-C data. And from this result, we can also see that some methods cannot control the FDR, and Clipper has higher power than other methods. So from all these real data biological applications, we can see that Clipper can be very useful in biological applications. And to summarize, so we want to show that Clipper avoids the need for valid null distributions and high resolution p-values. And from this, it can have some benefits over existing bioinformatic tools. So it has broad applications in high throughput data analysis. And the key part of the application is the definition of contrast scores. And we also want to echo the importance of validating the FDR control, because FDR control is just assumed but really validated validated in most bioinformatics methods. And in the future, we would like to further improve the power of Clipper by incorporating feature covariance or choosing the best definition of contrast scores, so that we can implement Clipper in more bioinformatics analysis. Okay, finally, I'd like to thank my advisor Jessica and Yilin, who worked with me to finish this project. And I also like to thank my lab mates and people from City of Hope who gave us the benchmark dataset for peptide amplification. And I also like to thank Dr. Whaley from UCLA, who is the co-author of the Max paper and gave us very important suggestions in the analysis. Okay, thank you all for listening, and I'm welcome to any questions.